Let's now understand when we can solve A transpose Y equals A transpose A, C, using the method of taking the inverse of A transpose A. Now, in order to take the inverse of this, we know that we need to require that the kernel of this matrix, so by the way, if A is a D by K matrix, and again, D is typically much, much larger than K, then we want to know when this exists. So one of the situations when this exists is when the kernel of this matrix vanishes. That's one of the criteria. So 0 as a vector space, as a vector subspace of Rk. So when does something like this happen? So to understand when we can apply this method, let's suppose that this is the matrix A. A goes from Rk. This is Rd here. And this here is the image of A. If we take the orthogonal complement of this image, in this case, unfortunately, I can only draw the orthogonal complement as having a single dimension, but you could imagine that it has a much, much larger dimension, especially if D is much, much larger than K. So the first claim that we'll prove is that the orthogonal complement of the image of A equals the kernel. Now, in order for this to make sense, I need to take the kernel of some matrix. Now, the image of A is in Rd. Its orthogonal complement is also in Rd. And I can't take the kernel of A because that wouldn't make sense. The kernel would live here. So I have to take, the only other thing I can take the kernel of is maybe the kernel of A transpose. So we'll do that. So we'll take the kernel of A transpose. And it turns out that these two are equal. So how do we see this? Let's visualize A as a matrix of vectors, so A1 through AK. And when we take the transpose, these columns just become the rows. So we'll do this proof just by showing that one is contained in the other, just to make it very explicit. So suppose that the vector V is, let's start with being an element in the orthogonal complement. So let's say V is perpendicular to A, the image of A. And then let's see if it's in the kernel of A transpose. So when we take A transpose applied to V, what do we get? So we'll write the matrix A transpose. Now we take these columns and turn them into rows. And we apply it to the vector V. But matrix multiplication tells us that when we do this, we take this row and multiply it by this vector. In other words, we take the dot product. So this equals another vector, and it's a vector in Rk. And what we get is A1 dot product with V as the first entry, all the way down to AK dot product with V. But if V is in the orthogonal complement of A, then it has to be that all of these dot products are 0. So this is actually the 0 vector. And therefore this containment holds. The orthogonal complement of the image of A is in the kernel of A transpose. So that shows half of the theorem. Now let's suppose, so conversely, suppose that the vector U is in the kernel of A transpose. Then by the same argument, being in the kernel of A transpose U equals 0. But A transpose U is A1 dot U. all the way down to ak dot u. But the 0 vector says that all of those are 0. And because the image of A is spanned by the vectors a1 through ak, we know automatically, by the same exact argument, that u is perpendicular to the image of A. So it's almost the same argument, which is why I'm not writing it. And therefore, this containment holds. And that's the other half of the theorem. So that's the proof that the kernel of A transpose equals the orthogonal complement of the image of A. Why is this useful? It's useful for the following very important reason. And it says that the kernel of A equals the kernel of A transpose A. You can already see why this is going to be useful, because instead of looking at the kernel of A transpose A, which we take two matrices, multiply them, it's going to be a little bit more difficult matrix to work with. If we could just look at the kernel of A, that would probably save us some time. So let's prove this. In one direction, it's pretty obvious, but I'll write it out anyway. So let's first prove the direction that the kernel of A is inside here. So let's prove this containment. So if U satisfies AU equals 0, then A transpose A U, because this thing is 0, also equals 0. So that direction is pretty straightforward. Let's look at the other containment. So suppose V satisfies A transpose AV equals 0. Then what this means is that AV is in the kernel of A transpose, i.e. AV is in the kernel of A transpose. But by the previous claim, the kernel of A transpose equals the image of A, taking the orthogonal complement of the image of A. So what's the picture here? Actually, let's go back right here. So we have that AV, which by the way is in this plane, also is contained in the orthogonal complement of that image. And the only vector that's contained both in A and in the orthogonal complement is the 0 vector. This implies that AV equals the 0 vector. In other words, V is in the kernel of A. And now the containment has been shown in both directions, and that's the conclusion of the proof. And let me just write out the final corollary, which is the useful one for us. It's like corollary 2, is that at least, so let's say A transpose, how do I say this? A transpose A inverse exists if and only if the kernel of A is trivial. So it's only the 0 vector. Now, why is this reasonable? So this isn't really an example. It's sort of an idea for why this usually occurs when you're trying to fit data. So our matrix A is typically going to be of the form F1 x1 dot 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 F xk Fk x1 all the way down to F1 xd Fk xd. So typically our matrix A looks something like this. And what would it mean for this to have trivial kernel? It would say that none of these, so all of these vectors are linearly, the set of these vectors, the column vectors, are linearly independent. Is that likely? So when might something like that happen? So for instance, if one of these functions did depend on the others in a linear way, so for instance, in the last video we said that we assumed that these functions were linearly independent. if they were dependent, what could happen? One of these column vectors could be expressed as a linear combination of the others. And therefore, these columns would be linearly dependent. And if these are dependent, then this has a non-trivial kernel. So that's at least that's at least one condition. That's a necessary condition for this to have a non-trivial kernel. So we demand that these functions are linearly independent. But furthermore, not only do we ask that these functions are linearly independent, but it also implies that these specific vectors, after we apply our data, are linearly independent. But if d is much, much, much larger than k, we only have very few of these vectors, right? So the number of entries is d, but we only have k vectors. So it's kind of easy. If you arbitrarily and randomly chose k vectors in a very large dimensional space, randomly, with almost surely, it will be that those vectors are linearly independent. Think about it. Just choose random numbers. So for example, let's write pi e 1, 2, square root of 3, 3, and the vector 1, 1, 1. I'm pretty sure that these three vectors are linearly independent in R3. And I randomly chose them. So even if d is not drastically larger than k, but even if it's just greater than k, almost surely you'll pick linearly independent vectors. So if your data is sufficiently distributed well and it's not lying exactly on one line or something like that, then chances are these vectors are linearly independent. So that's where it's going to be useful. And in the next video, we'll actually apply this to a simple example that you probably don't need a calculator to compute with.